desired byproducts, let's call them impurities, and we had to define what the yield of that process was, say in percentage or as a fraction. Now the problem is this: you can define yield in many different ways. Just as you can define efficiency in various ways of a process, efficiency of a process, depending on what you normalize it with, for instance, or depending on what you choose the output to be. Efficiency also has many definitions. Similarly, yield can have multiple definitions. Now, different books define it different ways. I have a penchant, a liking for a particular type of definition. So what we want to do today is show the book definition, which I don't like. Whether it's Himmelblau, Felder, and then I'll tell you the way I like the yield of the reactive process defined. We can take a multiple reactions problem and we can try to calculate the yield coefficient based on the definition that I have preference for. Is that all right? Is that okay?
Yes, sir.
Okay. Am I audible? I just looked at that lecture. The audibility of my voice sound was very, very low because there's no microphone, I guess. Am I really audible at all?
Yes, sir. Yes, sir.
Yes, sir.
All right, very good. Okay, fine. So let us see the book definition, which I don't like. Let's open it. So from now on, our discussion will all be on multiple chemical reactions, what we wanted to reach. And once we do mass balance on this, November, we shall also do energy balance for a single reactive reaction and then for multiple chemical reactions, right? Okay, there was no difficulty with fractional conversion, correct?
Yeah, no, sir.
Moles reacted by moles fed, there was no problem with that. How to find limiting reactant, how to find excess reactants, that also we have discussed last time, and you have solved and you know how to calculate percentage excess of all the other reactants other than the limiting reactant, which is the reactant which gets completely consumed, right? That's how we define. Okay. Now, is this visible? So the denominator is several lines. I don't like it one bit. So numerator for the yield is all right. We have a desired product. So So we want a ratio so we can have moles of that desired product formed in the numerator is fine. Now the denominator is moles that would have been formed if there were no side reactions and the limiting reactant had reacted completely. Now this is a different definition. So what it is saying is, suppose I had complete combustion of alkane and I had some other side reaction. You don't worry about that side reaction, just find the theoretical yield if there had been no side reactions, just from that complete combustion equation. Now, that's not the way we want to define product yield. If you define it this way, you will get a different, this is a fraction. So if I multiply by 100, I will get a percentage. I will get a different number than if I define it differently. Now we are particularly interested in, recycling unconverted reagents, right? Once you have a notion of fractional conversion, it implies that there are unspent reactants, unconsumed reactants. Unka kya kare hum? We don't want to leave them in the flue gas. That is a complete waste of energy and material. So normally we said we recycle that. So the problem now for us is, when we recycle to the fresh feed, we will form a combined feed. So should I define the yield based on the product form and the feed which is combined and entering the reactor, or the fresh feed? Or should we define it the way that is there on the screen? Now, so that means there are three different possibilities. The one that you are seeing on the, which is, we never did considered yield this way. I don't mind if you define it with respect to the fresh feed that enters the reactor. Well, not enters the reactor, fresh feed that is fed. Let's put it, let's get the term right. So the numerator of the yield remains the same as above, as here in the slide, but the denominator is the moles of limiting reactant that is fed, of the fresh feed, moles of fresh limiting reactant in the fresh feed. It's a very nice definition, I think. But the reaction engineers, they don't like this definition at all. This is fine for our mass balance purposes. What they say is, I am interested in how much limiting reactant is consumed. So they want to define the yield percent based on consumption of the limiting reactant. So in other words, for them, the numerator still remains the same. Numerator is the same in all the three definitions. But now the denominator is the moles of the limiting reactant consumed. Now this is the most commonly used Levenspiel type of, he has a book called Chemical Reaction Engineering, which we also followed. It's in 10th or 12th edition, and there is Fogler's book now in I don't know how many editions from Michigan. They are the two books that are very commonly followed. So they use this type of definition. So let us please write down. I think you need to write down the correct. I don't mind any of the latter two definitions. So let us distinguish between the two definitions and write them down. So the yield for us will mean number one, definition number one. Let's call this yield based on feed, okay, because fresh feed per dependent है. So yield based on fresh feed we define as moles of desired product formed, same as numerator here, divided by moles of limiting reactant fed. Moles of limiting reactant fed. That is our yield based on feed. The second definition, which also I am all right with, is the yield coefficient or percentage based on, or fraction, yield based on reactant consumption. So this we define as yield based on reactant consumption is moles of desired product formed divided through by moles of limiting reactant consumed. In all the three definitions, we are worrying about the denominator being different. Everyone looks at the limiting reactant. One definition that is on the screen doesn't worry about the other reactions at all. Don't worry about the byproduct reactions. I don't like it. That's fictional. That's a fiction. We should call it fictional yield. The other looks at economics, meaning कितना limiting reactant आपने feed किया, fresh feed. And the reaction engineers say, I'm not interested in economics. I'm more worried about what the reactant gets as input. So they say how much limiting reactant is consumed. The good thing about definition number 3 and all is that, it can be very easily generalized to a continuous process. We will see how to do that. Okay, so you got those two definitions. The denominator is either moles of limiting reactant fed or moles of limiting reactant consumed. So one is a yield based on fresh feed. The second is a yield based on limiting reactant consumption. Because जो fresh feed में है वो सब consume तो नहीं होता है ना. ठीक है. The definition of selectivity on the other hand is the same always. And there is no ambiguity there. As far as I know, there is only one definition for it. So it's just desired product form by undesired product form. How many mole upon mole? It's a ratio. Okay. So now let us look at a question. We will modify that question so that we can use not the one that I display, but I'm going to modify the question and ask you to find the yield based on the two definitions that we have used. Is that all right? Okay. So we start with two reactions. We have to find yield and selectivity of a dehydrogenation process. The second one is the side reaction. But I'm going to change the problem statement somewhat. Anyway, take those two reactions. He already gives you a fractional yield, but his fractional yield is calculated based on that first definition, 0.471, which I don't want to use. So let us flip this problem over. So I just have a modified statement. Please take it down. Reactions are the same. Ethane going to ethylene plus H2 and ethane producing side reaction to 2 moles of methane. And let us say this is taking place just like this problem statement at steady state in a continuous manner. Now, please write down that the molar flow rate of the feed stream, we should say, because there are also some inerts, no? It's not just pure C2H6. There are also 15 mole percent inerts. So the feed stream is, let us say, 100 kg moles per hour. So feed stream is entering at 100 kilomoles per hour. Similarly, product stream is exiting at a certain flow rate, and let's say that is also given to you. So that product stream, it contains a number of species. We have to we will identify them, and the total flow rate of that product stream is 140 kilomoles per hour. In other words, incoming flow rate 100, outgoing product stream flow rate 140 kg moles per hour. Now we are given the composition of the inlet stream, feed stream. It's given 85 mole percent of C2H6, 15 mole percent of inerts. Now similarly, take down, let us say we do exit flue gas analysis, and we can obtain the mole percent or volume percent of the exit or product stream. So that is given to you. Please take down C2H6 in the stream is 30.3%. C2H6, the main product is, sorry, not main product, unreacted ethane is 30.3%. The main product C2H4 ethylene is 28.6% mole percent. H2 hydrogen is 26.8%. Methane 3.6%. And inerts 10.7%. That total should add to 100 mole percent. C2H6 30.3, C2H4 28.6, H2 26.8. Please check CH4 3.6, inerts 10.7. Now what you have to find is the fractional conversion of ethane. First question. What is F? Small f. That's first. Then second, find the yield of ethylene based on feed. Third part, find the yield of ethylene based on reactant consumption. Fourth, find the selectivity of product, that is ethylene, relative to methane. Find the selectivity ethylene मोल मिथिलीन पर मोल मीथेन. इसको आप ट्राई करिए. Using the type of method we have outlined several times now. So first you have to draw a diagram. So now N1, N2, N3, N4, N5 you know, or at least as mole fractions you know. So Y1, Y2, Y3, Y4, Y5 you know. Because that is given in the product composition. So just modify this figure to suit our new problem statement and write down from
So
the
I have a
flue
doubt.
gas analysis. Yeah.
So for the fractional conversion, will we consider the ethane that got converted to methane as well?
Well, you have to find out how much of the methane is consumed per hour. So of course you have to consider both the reactions.
Okay.
You must fractional conversion means kitne, how many kilomoles of methane you fed, not methane, ethane you fed per hour in the denominator, and how much of that percentage or fraction got consumed per hour. Whether it is consumed to make the desired product or methane or indesired product is irrelevant. So you have to include the consumption. It's always based on consumption upon feed, small f. I tried to talk. I'm almost shouting louder. But does it make any difference to you all, or it's the same as earlier?
So it's pretty much the same.
Huh?
It's pretty much the same.
Okay, but because I today for the first time I looked at the recording, it was highly inaudible. I mean, inaudible means usko bilkul silent. There can't be. There's a lot of construction work here. If there's noise, you can hardly hear. So I'm just speaking up. I don't know if it helps. Maybe I need to get a microphone. Anyway, as long as you can hear, I'm fine. So take the basis as the given flow rate. So 100 kilomoles per hour. That looks perfectly fine. And now look at how much is there in the feed, how much is there in the product for every component. And then you can balance, say, ethane and other species, right? So per hour, how much of the ethane is flowing in?
$81 kilomoles.
Right. Now, can you find out the consumption of the ethane?
Yes, sir. So of course 30.3% was left unreacted.
Correct.
So that's 42.42 moles.
Right. So that's the output.
Yeah, and so if you subtract that from 85, you will get the moles reacted.
Correct. So that will
That's
be the kg mole
42.58.
C2H6 consumed per hour.
Yeah,
So find that out.
so 42.58.
Right. So approx 42.6 kg
Yeah,
mole consumed per hour. From this we can find small f.
yeah, 42.6 or 42.58 by 85. That's approximately 50.9, 50.1.
Mole per mole. Mole
Yeah,
consumed per mole fed.
yeah,
Very good.
50.09%. So that's like 0.5.
Right. So 0.5 is your conversion. Similarly, can we find for ethylene?
Yes, sir, like 28.6% of 140, that's 40.04.
So that's the kg moles ethylene per hour in the exit flue
Product
gas.
stream. Yeah.
All right. Do the same then for methane also.
Methane is 5.05,
Because
5.04 mole.
140 into 0.036.
Yeah, 5.04.
Very good. That many kg moles of methane per hour. Nice. Is there any ethylene or methane in the feed?
No, sir.
Right. So these quantities that you calculated, they refer to the hourly rates of production of both methane and ethylene, because they are the as well as the output flow, right? Because input is nothing, output is just what is generated. Because input minus output is what is generated. Or rather, output equal to generation in this case. Input minus output plus generation is 0, right? So output equal to generation. Now can we calculate the yield coefficient also?
Yes, sir. Like for yield based on feed, we just have to have like the moles of ethylene formed by moles of
Per hour. Yeah.
ethane fed.
So find the moles of ethylene produced per hour and divide it through by how much of C2H6 you fed, which you already know because that's your basis. Which one do you expect? Do you expect the yield based on feed to be larger or the yield based on consumption?
So consumption.
All right, very nice. By how much? You can always first calculate one and then the other.
So based on feed, I got like around 47%, and based on reactant consumption, I got around 94%.
Right. Why is that? Because in the yield based on feed, the 40 kg mole per hour that was produced is divided by 85, right? So that is what you
Yeah.
fed per hour. However, what was consumed was only 42.6 or 42.58 per hour. So naturally, the yield based on consumption is almost double in this particular case. So yield based on feed was 40 divided by 85. Yield based on consumption was 40 divided by 42.58. Whatever you get, 0.94 or so. Similarly, you can now find selectivity also.
Yes, the selectivity will be 40.04 divided by the moles of methane produced, that is
Correct.
5.04.
Approximately 8
Yeah.
moles per mole. That is the selectivity of this process. Obviously, the yield and the selectivity are so defined that we want as high a number as we would like. Okay, so this was fairly straightforward, but we just wanted to illustrate these ideas because again and again we will use them. Now, what we need to do next week, one, we want to extend this notion of yield based on feed, yield based on reactant, limiting reactant consumed, and selectivity to combustion reactions, which may have more than one reaction in principle, 2, 3, 4, depending on incomplete combustion, what are the byproduct reactions. I think that is also fairly straightforward. I'm sure you will be able to do it. But a more challenging question that we want to take up next week is as follows. Suppose you had a reactor, and then let us say you had a separator unit, like what we were doing in series with the reactor. Once again, you could not convert everything. So you recycled the unconverted stream back to the fresh feed input. In other words, you had a mixed flow rate to the reactor. So you have a reactor, a separator, and a recycle. And now, unlike earlier, we also have chemical reactions taking place. Now, how do we define conversion? I'm not going to talk about yield right now. Let us say how to define conversion for such a situation where we have an analysis of chemical reactor with product separation and recycle of all the unconsumed reactants. That is a more interesting question. So in other words, what we are doing is extending earlier non-reactive system to a situation where a chemical reaction or more than one chemical reaction is taking place. And it is a continuous process. So the problem now is this. I mean, how do I put it in words? I mean, on one hand, you have a process which is a composite of reactor, product separator, etc. on the other hand, as far as the reactor is concerned, every time you continuously flow the mixed stream of reactants into it, it will have some conversion and you will get some output from the reactor. So in principle, we can also, as far as the reaction engineer is concerned, he says my reactor is working well. इतना conversion हमें मिल रहा है. However, the overall conversion will not be equal to this. So we will have to carefully distinguish between, we have to give some nomenclature to the overall conversion and the conversion as far as the reactor is concerned. And then take a reactor reaction and then actually calculate these things. And then I guess we can take multiple reactions as we do in combustion. And there's no end to the number of complexities that you can do. But the moment you take multiple reactions with recycled, then of course 1 hour is not sufficient generally. At least for a minor, it's not sufficient. So this is what we want to do next week. And that in a way is the end of, as far as we are concerned, mass balance, what we want to do in the time available. And then November, we need to go to energy balance. And don't forget that mid-sem break from 29th and 13th onwards, I won't be here. So I said that we will take a Sunday or two and complete the biological part. So after we do the, so between 15th and 26th, I am not here. So we will complete the biological part in over 1 or 2 Sundays. That is what I told you in class number 1, right? So that way you will have all the entire syllabus more or less done, and then you only have to worry about your presentation. And you would have a smattering of mass balance, energy balance, and for chemical systems and biosystems, and you can easily form a group. And I suggest you form a group earlier, and then you can choose a topic, and you will have the whole mid-sem break and another 12 days. Then we can start on 27th, that which is the last 20% of your thing. So we will try to complete everything by the break.
Sir, please list the topics for the presentation earlier a little bit, so that we can plan for the presentation.
You have to decide. You have to decide. It doesn't matter for me. It doesn't have to be what we cover. You can take any flow sheet. You can take any product. Generally, the 2 products, I mean, from my experience, you don't have to do it. I mean, the stuff that by chance repeatedly I had done long back. I mean, at IIT Kanpur, one is urea production, urea fertilizer plant. And we had taken quite a large, I mean, that's just too complex. I mean, we had taken the entire IEL plant, you know, that uska mass balance, I don't expect you to do a whole plant, okay? That, and the other thing on which I had considerable experience was the humidification and dehumidification. But then you don't have to do that. You can choose what you want. But those are the 2 things that I had personally done. Just to give an example, you can choose whatever you want. Yeah.
Excuse me, sir. Hello.
Yeah, I can hear you.
Sir, can you tell about the presentation thing again? Actually, I joined the course a bit late, so I don't know.
It's just 20%. We have to keep, we cannot keep minors, majors more than 80%. So, I mean, again, keeping another exam doesn't make sense. So what we decided is that you will form a group of 5 to 6, I think 5 students, 6 students, up to 6 students. And you will jointly present from 27 December onwards over 3 classes or 4 classes, whatever is left, on that one topic that you choose, on which you would have done a mass balance or an energy balance or a combined mass and energy balance on a problem that you have enough time to decide, and that too as a group. So that presentation of say 10-15 minutes is 20%. Anyway, we are still far away. That is far away, but you make your group. Last minute में फिर time नहीं मिलेगा ना, because I am out from 14 to 20 and come back, and back we are on 27th, and then we will have some 3 or 4 clouds में आपको present करना है, because that has 20%. Now that attendance, everything has been removed.
Okay, sir.
So what I will now continue with next week is all these recycle systems with chemical reactions. So what all we have done till now is define all the for a reaction, what is fractional conversion, what is yield, what is sub yield, that is yield based on product, reactant to the consumed, yield based on feed, selectivity. You know how to do it for a simple case like you did today. Now we are going to add some more streams such as recycle to it and have a reaction and combustion, which combustion reactions, and then again calculate all of these things. Okay, and let's see if we can finish by next week. That would be very nice. So all of October mass balance, then November onwards we start the energy balance, and then December what we want to do biological we are going to do over a couple Sundays. Okay, so we continue on this and go to combustion reactions or some other reactions, and then add recycle streams. Okay, in other words, it's an extension of what we did, but now with not just unreactive systems, which are not very interesting to me, but actual chemical reactions, and we find all of these mass balance and all of these yields, and which are important numbers, selectivities. Okay, all right, we continue on this next week. Thank you.
Thank you, sir.
Yes.